You're going to get used to this throughout the course, but in grade 12 physics, most often the vectors that we're working with are not going to be nice, straight back and forth vectors. So in grade 11, if you took that course with us, then your every vector was east-west or north-south, and everything happened on a flat surface. In this course, we throw all of that out the window because the world doesn't work that way. Not everything moves east-west and north-south. And so even with starting with relative motion, you're going to get vectors that are not perfectly back and forth. So let's try a couple examples of those. A river with a current is moving from west to east at a speed of 5 meters per second. A boat pointing from south to north is moving at a speed of 10 meters per second relative to the water. What is the velocity of the boat relative to the shore? So, a couple things are happening here. The current is moving west to east, so we know that our river is oriented like this. I'm going to make it nice and wide so I can draw a boat in there. Okay, and we know that the river velocity is flowing west to east at 5 meters per second. So I'm going to draw that right here. There's our river velocity. So I'm going to call that VR. Sure, doesn't really matter, but that's the river velocity, which is 5 meters per second. And then we also have a boat that's on the water. The boat is traveling from south to north at 10 meters per second relative to the water. And so what that means is if you were on the water, moving along with the water, you would see the boat traveling straight north. Okay, and so that means we have to take into account when we're talking about the boat's actual velocity relative to the shore, we have to take into account the fact that the boat is moving north. We also have to take into account that the current is bringing it east. Okay, so both of those things are happening. So on the river, our boat velocity is 10 meters per second. And since that's relative to the water, we also have to take into account the river's velocity. So this would be, we'll call it VB, the velocity of the boat. I don't know why the river's velocity is a lowercase r. We're going to go with it. So there isn't a good formula, like we did in the previous section, that kind of makes a chain of relative velocities to get your final answer here. That's not the best way of doing this, because you're going to find yourself getting confused. So you can use the exact same method we just used above to figure out the velocity of the boat relative to the shore, but that's maybe not the best way to think about it. Okay, so this is a vector addition problem. We have the river flowing 5 meters per second east, and we have the boat moving 10 meters per second, not drawn to scale, ran out of room, 10 meters per second north. And then the total velocity that we're going to find the boat traveling at is a combination of those two things. Okay, and we will also need to give the direction as well, because that's part of velocity. So this is the velocity of the boat relative to the shore. VBS. Maybe an unfortunate subscript, but hey, that's life sometimes. So when we are figuring out that velocity, it's a squared plus b squared equals c squared. We have to use the Pythagorean theorem. So VBS is equal to the square root of 5 squared plus 10 squared. And when you do that, you get 11 meters per second. And then we need a direction on that. And so we're going to use the inverse tan of 10 over 5. Okay? Theta equals the inverse tan of 10 over 5. And you get an angle of 63 degrees. So our final answer here is going to be 11 meters per second. And we're starting measuring this angle toward the east. That's this vector right over there, and we are measuring it toward the north. So the angle I'm going to write down, or the direction I'm going to write down, is east 63 degrees north. Now you could have also drawn this triangle differently. You could have drawn your 10 meters per second first, and then on the end of that you could have drawn your 5 meters per second, and then you could have put in your resultant right over here. And so then the angle you would have gotten would not have been 63 degrees. You would have then gotten 27 degrees, right? Because then you would have done the inverse tan of 5 over 10 instead of 10 over 5, and you'd get 27 degrees instead. That is just as valid. You just have to make sure that you then write as your direction north 27 degrees east, because north 27 degrees east and east 63 degrees north are the same direction. Part B, same situation. Suppose the captain of the boat does not want the boat to be carried off to the side with the current. Instead, he wants the boat to travel straight across the shore. Or she. Captains can be anything. What velocity will the boat appear to be traveling with reference to the shore? At what angle should the boat travel to accomplish this? Okay, so this one is a little bit different, but it still has everything to do with vectors. So let's take our river diagram again. Here's the river. And now we want our final vector. Let's make it red. Let's make it green. We want our final vector to be like this. Okay, so we want our north-south vector plus our east-west vector to add up to this thing. Okay, that makes it a little bit more complicated because our original was, let's use this thing. This was our 5 meters per second. This was our 10 meters per second, and this was our resultant. Okay, so because of the velocity of the river, 5 meters per second, it was being carried off to the side instead of just going 10 meters per second straight north. Okay, now what we want to do instead is use that 10 meters per second that the boat can travel at and not make it perfectly north and south, right? Because if the boat captain sails perfectly north, we know that the current is going to pull him off to the side. Okay, so we actually want to counteract that current by changing which way we are sailing. So instead of sailing straight north, if I want to move straight north, I'm going to have to point myself this way, right? Because then the current is going to pull me back this way, and my total velocity is going to end up being straight north. Okay, so I have to figure out what direction should I be traveling, and what velocity would I seem to be traveling with according to the shore. Okay, so here's what we're looking for. We're looking for what heading should I use, what direction should I point, and what is my total velocity? How fast am I actually moving toward the opposite shore? We're looking for those two things. Okay, this is a right-angled triangle still, right? So this is where we would be heading. That's the velocity we can actually sail with. This is the velocity of the river, that 5 meters per second. And then this will be our resultant, the velocity of the boat relative to the shore. And so this is 10 meters per second, right? Because that's how fast we can actually sail this boat. So now all that's changed here is that we know the hypotenuse is 10. Rather than knowing the opposite and adjacent sides and then figuring out the hypotenuse, which was the resultant, right now we know the hypotenuse and the resultant is actually the adjacent side. Okay, this is the angle we're working with right now. So what we're trying to do is counteract that 5 meters per second that's pulling us to the east by giving ourselves 5 meters per second velocity toward the west. Okay, so if we would split our 10 meters per second into components, part of that would be 5 meters per second toward the west, and the other part would be whatever velocity we're actually traveling toward the shore with. And so this is also VBS. Okay? So we can look at it two different ways. Way number one, which I've drawn in bold over here, you can say that the 10 meters per second is the hypotenuse, and then you can solve for the adjacent side, and the VBS over here would be the adjacent side. Or you can consider the 10 meters per second to be the hypotenuse, and you're splitting that velocity into its components. 5 meters per second is counteracting the current, the word escaped me for a second, and the other component, whatever that is the velocity we will actually be traveling with to the other shore. Okay, so I'm going to use the bold version, but you can use the dotted line version if you want to. No big deal. We're still doing VBS is equal to the square root of. So let's think about how we were setting this up. If that's the hypotenuse, we have to do c squared minus a squared equals b squared, right? Because we're looking for the adjacent side, we're looking for b or whatever. You could have made it a if you wanted to. We have to make sure that we are doing c squared minus a squared in the square root here. And so our c squared is 10 squared, and our a squared is 5 squared. And so the velocity that the boat is actually traveling across the water with is going to be 10 squared minus 5 squared. And if you do that calculation, I just really like writing VBS. Something about it. It's 8.7 meters per second. Okay, so that's the velocity with which we are traveling to the opposite shore. Okay, and the reason that we're asked for the directions separately is because this VBS is perfectly across the river. So this is just north. That's how fast we're moving to the opposite shore. Okay, and so the second part of the question is asking, what direction do I need to be pointed at in order to make that 8.7 meters per second happen? And so I'm going to figure out this theta over here. I'm going to use opposite over hypotenuse. I'm going to use sine to do it because I prefer to use unrounded numbers. I prefer to use the original values in the question to do that. It gives me a better, more accurate answer. Okay, so I'm going to use the inverse sine. I should make this an equation. Theta equals the inverse sine of opposite over hypotenuse, which is 5 over 10. And that equals 30 degrees. You may have that memorized, that 5 over 10 is 0.5, and the inverse sine of 0.5 is 30 degrees, or the sine of 30 degrees is 0.5. That works too. But this is where we need to be pointing. Okay, we should put directions on that. So we should be pointing north 30 degrees west. Okay, that's our heading. That's not going to be the direction that we are actually traveling. We are actually traveling straight north, but the north 30 degrees west is our heading. It's where we are pointing.